Hello, welcome to this new webinar. Today we will talk about the release highlights of CivilFEM 2021. Roman Martí and myself, Ronald Siad, will be the ones presenting you these new developments and implementations for this upcoming version. As well, we will talk about the beta tester program, so everybody is invited and it will be very welcome to use the beta version of this new CivilFEM. So stay tuned.
Well, the release highlights you can see in these slides are concrete user design sigma epsilon diagram, the diagram that is used for post-processing design, second design the codes that could be editable and also modified by the user. We'll see in details this what it could be used for. Also, the improvements in the thermal structural couple analysis, and also some new nonlinear temperature-dependent material properties that we have implemented based on codes, and also other improvements are the congruent mesh and some improvements of meshing options. For the springs, we have added activation and deactivation options that can be activated and deactivated for a stage and evolutive and construction process. Also, 2D solid sections. Solid section is a cross-section that is performed in solid element models where they are integrated to obtain forces and moments in the same way as if they were a beam for design. And the last main release highlight that we are having is the hardening soil model and the small strain overlay model, two new geotechnical material models. They will not be available in the first 2021 version, 2021 release, but they will be in the upcoming versions during these years in the following months. Well, we are going to start taking the concrete user design sigma epsilon diagram. Just before seeing that, I will do an update of what CivilFEM already has for the concrete. In the concrete, we have the diagram for analysis and also for design. For the analysis, are visiting the solution level, and they are for nonlinear analysis. So we have different stress-strain curves that are used for solving nonlinear models with cracking and crushing behavior. And so we can determine a cracking stress, the compression stress-strain diagram, also other data for nonlinear analysis. Here we have from a previous webinar we have uploaded in our channels. This is a concrete beam where we have some loads, and here this is the CivilFEM model, and we can see that crackings are happening and the stress forces versus displacement curves that are obtained are exactly the same from the real test and the CivilFEM development. So well, here you can see in the model cracking are happening until the collapse of the beam, having this force versus displacement relationship. Well, this for this nonlinear analysis, we also have the post-cracking behavior that can be defined after the crack stress. We can define different post-cracking behavior for solving and analyzing the fiber reinforced concrete behavior. So in this case, we have two beams that we are comparing. In one of them, there's a lack of shear reinforcement, and we apply some loads. In one of them, there is no fiber reinforced, and in the other, we have. And we can compare for the same loads. We can compare different behavior. Here, cracking are happenings. Here, cracks are more reduced. And here, the failure is due to this shear crack that is happening. And here, for the same loads, there is no failure. We have to increase it. And the final failure is due to the bending crackings. So, well, that is for solving. The latest developments we have done for improving all this concrete analysis is at post-processing level, at the post-processing design. So, well, here you can see that you can add, this is a plot from the from the material properties. In the material properties for the design diagram, that is the diagram that is used for code design and code check and design to calculate reinforcement amounts and so on. So here we can add different stress-strain relationships. Here in example for this low fiber reinforced concrete, we have a part of the parabolic rectangular behavior for compression. We can give some remaining stiffness for tension. And we can use this these laws for designing to calculate if any structure can need a part of the fiber reinforced, if any structure could need extra reinforcement, a part of the fiber reinforced. Just we are going to see this the applicability of this new tool with this example. This is a hyperbolic shaped roof. This is a building that was made by Felix Candela. And well, it is amazing of how slender this roof is and how well it works under overloads. So well, okay. So if I open the software, here you can see we have modeled it just with boolean operations, tracing different lines. We have generated this model in a very fast and easy way. And then we have meshed with shell elements for different parts of this, and every of these cell elements has a thickness of only 4 centimeters, so it's very slender. So the concrete is C4050, the concrete we have used, and as I said before, we have set 2 different behaviors, one for solving, nonlinear analysis for solving for solution level. We already have, CivilFEM already had, and you can find different webinars where we explain a lot about that. And just we select it here, material tools. We could click in analysis options and then check instead of linear, short-term loads, and just create all these options for solving. In this case, I'm going to leave linear analysis, and also what we are doing is adding different design diagrams. For the design diagrams, we have the default, the stress-strain diagram is the one that is defined by the AFTID code. In this case, the AFTID code is the Euro code, so you can find the Euro code stress-strain diagram. One of them is the bilinear one, that is defined by the Euro code. You can use it, or the default option, that is the parabolic rectangular law. So these are the 2 different options, and I have added 2 extra behaviors: low content of fiber reinforced concrete, and here you can see for 28 days we have added parabolic rectangular compression curve and a remaining tension stress of 3.5 megapascals. Also, I have added another behavior for high content of fiber reinforced concrete, and I have added this behavior, which is also parabolic rectangular compression law. There's also for tension, there's a cracking stress of 3.5 megapascals in the same way as the previous one, but then there's a hardening part and a softening part of this behavior. So the tension stiffness of this concrete is higher. So what I can do is check and design this model for different concrete types. The first one I'm going to use here, the AFTID one, is going to be the bilinear Eurocode 2 behavior. So just after solving, I have created a combination, self-weight plus snow, and after solving, check the results, and I'm going to post-process to check the shells. Check cells by the orthogonal direction method and considering torsion plus in-plane shear forces. So I'm checking longitudinal reinforcement. Well, I'm checking if it could need longitudinal reinforcement. What I have done is just define the different shell elements for the different parts of the rule, but without any type of reinforcement, only pure concrete. So what I'm doing is checking the model, and we'll analyze if it is okay after checking, or if it will need extra reinforcement amount. So I'm going to plot checking results, and the results are criterion for X and Y direction. In this criterion, if I plot them, we can see criterion reach 4. This criterion must be less than 1. I'm going to modify the range in this situation. Discrete, and I'm going to set this value up to 1. So we can see values over 1 are not okay, and values under 1 are okay. So we can see that most of the model is not okay. They don't fulfill these values, and I'm going to check in the other direction instead of X direction of the reinforcement, Y direction. Also, I'm going to plot the results. Well, we can see that in this model also there's some parts in the other direction. Well, I didn't display X and Y direction are the two reinforcement directions. One is radial, the other is circumferential, more or less. So well, we can see that only colors, yellows and greens and blues are okay. So most of the model is not okay for this concrete. Let's analyze in one of the elements that is not okay. So I'm going to plot the iteration diagram of the element 5.3 in Y direction in example. And in this iteration diagram, we can see that we have some tension stress. So it is outside the iteration diagram. So this model is not okay. I'm going to try with modifying the concrete type, and I'm going to use for this behavior the low content of fiber reinforced concrete. Then selecting it, I can check the whole model, or I also can obtain the iteration diagram for those elements that I select. So I'm going to plot the iteration diagram for the same element, 5.3 only, and Y direction to compare results. So well, now we can see that now the iteration diagram, due to this fiber content, has a tension stiffness, and now the point is okay. So well, just for explaining that criterion we plot before, this criterion that you can see goes from 0 to 4. That criterion is the ratio between the center of the iteration diagram and our point and the ultimate load. The CivilFEM creates this line and then gives a ratio between the center and the ultimate strength and the action. If that ratio between the length of these two lines is less than 1, it means the action is inside the iteration diagram and the elements are okay. If that is outside, this ratio is greater than 1 and it is not okay. We can see that with this low content fiber reinforced concrete, the model is okay, and also if we perform a global checking of the whole model, check shells, orthogonal direction with this concrete, considering in plane shear and also torsional moment. This is the evolution of the checking analysis. So while performing that analysis, we will see if all the elements are okay or not okay. We are going to plot this contour plot. Okay. Now the result is this, and now we can see that now just colors. I'm going to reset the range. Now we can see that colors, yellow, greens and blues are okay, reds are not okay. So for Y direction, the model is okay, almost okay, just in the elements at supports are not okay, so they would need reinforcement. This is for Y direction. For X direction, we can see also the model is okay, only in these nerves here results is over 1, so it would need reinforcement. A part of the fiber reinforced that it already has. So well, the next step is designing. I'm going to design the model, considering both, considering in plane shear and torsional bending moment. And after the design, I'm going to just plot reinforcement amount that is needed for this model. Well, here we can see the process that is. This is the design results. So here I'm going to plot reinforcement top bottom in centimeters per meter. I'm going to plot the values and modify the range. So well, we can see that there's no need of reinforcement in the most of the model, apart of these points here where the reinforcement amount is calculated, and in this case is 20 square centimeters per meter at those zones. Also, well, I've only used, because this is a simplified model, I've only used cell models. You could also use here for these nerves beam elements for that part and design those beam elements, calculating reinforcement amount. And well, but basically the idea was explaining the design of fiber reinforced concrete structures that we can consider, modifying the fiber contents values, the stress strain diagrams, and calculating reinforcement amounts. Okay, well, if we continue with the next feature for the thermal structural couple analysis, we have increased the analysis result. We have strong couple analysis where we analyzing performing thermal analysis on every increment, and thermal results are applied to the structural analysis with thermal loads. Results are considered. The structural results then are considered in the thermal analysis, the deformed shape for calculating new thermal increment and so on. And well, a part of this strong couple analysis, we have thermalotropic material properties, thermal conductivity and specific weight. Also material nonlinear behavior, temperature, nonlinear temperature dependent properties. For the thermal analysis, we have convective, conductive, and radiation boundary conditions on any type of the elements, and then we can perform nonlinear steady state or transit thermal structural couple analysis, steady state or transit, and also for results, a part of the structural results we already have, we have all these post-processing heat transfer analysis results like temperature, thermal flux, thermal gradients with vector plots. Well, this is what we already have. The latest developments are improving the thermal structural strong couple analysis. It is solving faster and better. Also, we have added in the material library, we have added the stress strain laws that are defined by the Eurocode for concrete and steel. This is the compression stress strain diagram for concrete that is reduced with temperature from 0 to 1,100 degrees, where this compression parabolic law is being reduced, and the same for steel by linear steel laws that are modified. And also for the concrete, also the cracking stress is now, it is also a new implement that is temperature and time dependent cracking stress. That is an example for earthly concrete properties. We have all these options. So main applications for this is an example, the thermal stress in concrete and heat of filtration at early age for early age concrete. An example here, we are placing different concrete blocks and pouring this concrete, and analyzing for the first step is the heat of the due to the cement is creating excess of thermal stress, and also we can consider ambient temperature. This model is a dam with only ambient temperature, and these are two fire analysis to models. So these are main applications that could be used for this thermal structural coupling analysis. So seeing in detail here, this model, the early age cracking analysis in this concrete. This is based on an old example we also saw in a webinar. What we did is just activating a new layer of concrete. We have on top of this added the ambient temperature that is with the variation day and night, and also the effect of the heat generation from the cement hydration. So with this thermal analysis, on top of this point, we obtain this stress that is modifying. It is increasing due to the increase of the heat due to the cement hydration, and also due to the ambient temperature, we have this modification between day and night. Also, we are comparing with the new development tool, that is the time and temperature depending crack stress. That crack stress is this other curve. So with this model, we can check that at these zones, the stress on the concrete, the thermal stresses are over the cracking state, and we can see in those days where the cracked are development, and find in the model those crack development the same way we saw before. This is an example we can solve with CivilFEM. Another example we already did in a webinar, it's the stability of a steel bindle under fire, with some isolation for the steel for the steel. And in this building we apply a fire in two different compartments of the building. In the first one here we apply the fire, and this is the temperature low versus time on the steel part that is covered by this isolation. So this is the time that it reaches to temperature reach inside it. And in this building we can see that due to this fire, yielding is happening in those parts and the collapse of the structure. In the same way, we apply the fire on this other part of the building, in this department, and we can see collapse happen much faster and easier due to the buckling of those columns in these zones. So in this case, just if I go to the software, the way to define that, here in the material tool, in the analysis, we can see that we have the diagrams at elevated temperatures. Just selecting it, clicking OK. Analysis diagram, we can see here this table that are temperature dependent stress strain diagrams for concrete and for steel, based on the active code, but they can be they are editable and can be modified by the user. Okay. So next example is the same, is a concrete beam. Also, we are applying thermal loads and material properties based on the Eurocode for concrete and steel. We apply fire around it, and we get this result. In this case, where the temperature dependent material properties are thermal conductivity and a specific weight based on the Eurocode with these loads, and also this compression stress strain diagram, also temperature dependent properties. This is for concrete, the same for steel. And these are results. These are the thermal results for these elements, how the temperature go inside the model. On top of this, there is no fire, only it is applied on lateral faces. And these are the result of with the cracking and yielding result on the model. So we can see that due to this fire, yielding start happening on the model when temperature reaches reinforcement, and cracking is also happening until collapse of the structure. So we obtain time for collapsing this structure. What it was about 210 minutes.
The main mesh improvements are utilities to achieve a better mesh, conforming mesh or congruent mesh, and using automatic tools. So the user doesn't need to take so much time in this process. Okay. The congruent mesh, the new, here you can see a new button in this structure. You can see, well, I can open the software. Here it is. Here we have two structures. Once we select two entities, which can be adjacent. Okay, here you can see the new button, congruent mesh, can be mesh, standard mesh, or congruent. With this new option, here these are two dome structures, and the one on the right has it has its geometry. We'll see here, which is doesn't need to be with shared topology, and we have used the standard mesh. If we check the node connectivity, we can see here that the nodes of these are beams, okay, linear elements. The nodes of the beams and the shell elements, the plates, are not coincident. We can see the same here, the walls and in the foundation. So they have dissimilar mesh. In order to get, we can of course we can always use contacts, but if we want to obtain a conforming mesh, a congruent mesh with node connectivity, so we just select the elements to be meshed, and we click here congruent mesh, and you will see here, in this case better, okay, that the mesh is conforming for both wall and the foundation, and the same for the linear elements, the beams and the roof. Okay, this is one of the new capabilities, so we don't need to define shared geometry in order to obtain a congruent mesh. Okay. The next new capability is the parasolid mesh. This is a new property here, a checkbox. So if we want some refinement in particular areas, we define local mesh controls for these parts where we need a finer mesh. What about spring activation and deactivation? Well, as any other entities, in this case for springs, any type of springs, node springs, surface springs, rotational, now they have a new option, which are the activation and deactivation type, which are very useful for construction processes. By default, they activate day 0 and they never deactivate. But this is property, which it's used. Here you can see any other in materials, okay, in contacts, depending on your calendar time, okay, by default 28 days. You can change the time, so the properties of the materials will change. Materials, contacts, and now we have the springs as well, with the option of activation or deactivation at any time. Another new capability is well, once if we have a 3D model or a 2D model using solid elements. In this case, we have an example of a 3D model. All the piers, the foundation, and this hammerhead are all modeled by using solid elements, 3D solid elements. In case we need to perform a code checking, so we need forces and moments as results, we have the capability of, let's see here, capability of creating cuts, so we can obtain cross sections. With this new utility, CivilFEM will integrate the stresses of those sections, and we'll get forces and moments as results. Once we have those forces and moments, we can perform a code checking or design according to standards. So here we have these elements, these 4 elements. Well, we have neoprenes as well here in the connection, but here we have defined our different coordinate systems in order to capture the solid section for both the hammerhead, columns, and foundation. Okay, so if we have, here you have, this is the capability of solid section. We will have here our sections, which can be, of course, always reinforced with bending, shear, torsion. Okay, and we can define our reinforcement here, and the same for all the rest of entities. Okay, we have here more cuts. Well, depending on where the section is created, the section will have different tessellation. Okay, we will have these results, plot solid sections. Okay, and here you can see the forces and moments: axial forces, shear forces, bending moment, torsional moment. And later we can perform an axial bending check for solid sections, and we will have as result, for instance, the total criterion. As Roman explained before, it's a kind of a safety factor of the demand and resistance of the section. The solid section capability was already included in previous release, and for this 2021 version, the solid section for 2D is enabled. It is not in the summary of highlights, but there is a new type of geometry which can be imported, which is the industry foundation class data models, very well known for BIM. Okay, besides the already existing ones, the XF, IGS, Parasolid step, we have the IFC extension.
Well, for the geotechnical material models, we have for the latest developments are the hardening soil model, the very famous and popular hardening soil model, and also the small strain overlay one. You can see here the list of materials we have: linear elastic, darker Prager, can claim or Coulomb hook and brown for rocks, nonlinear elastic, hyperbolic. This is Duncan-Chan behavior, which is very, very similar to the hardening soil model results, and a small strain overlay. Well, this we didn't have time for having these two materials, small strain overlay and hardening soil model, in this first upcoming version of 2021 version, but they will be ready in the upcoming updates of this version, of this software version, so they will be available in this version. And well, as you know, this hardening soil model and this strain overlay are very suitable for this type of a structure where we have excavation and construction on the model with loading and unloading loads, also for retaining walls that they can have some displacements. And well, for this type of models, these material models are very suitable. Well, finally, the summary of what we have seen is that, as you can see, the thermal structural couple analysis and nonlinear temperature dependent mechanical properties was improved, now covering all sorts of analysis that are needed for civil structural analysis, because all properties are time and temperature dependent properties for the material, the mechanical ones and also the thermal ones. And we have the strong thermal structural couple analysis. For designing, we have the stress strain diagram for designing can be modified and can be added the stress strain diagrams for fiber reinforced concrete, low and high for different contents. Also, well, the rest of the examples Ronald explained are the congruent mesh and the improvements about mesh, the spring activation and deactivation. We have added a calendar time for activating and deactivating for construction process. Also the solid sections, we already have the 3D and we have added the 2D, and the new material models that are coming soon in the upcoming versions.
About training, well, first of all, we will talk about how to enroll to register to the new beta tester program for the 2021 version. To join the beta tester program, go to the finite element method free course. The beta tester program is already available in this website. If you go to the free FEM course for civil engineering, you will see the section for the beta tester program, and it's explained here well how is this focused. First of all, is to for you, if you're new in this platform, you will learn the software, but it will be the best if you test the new improvements, the ones that were explained in this webinar. There will be some guide examples here. As you can see, just for participating, you will receive a free training course and with a certificate, and as well a discount in the rest of the courses of this international CEA Education Center. And the winner will obtain a grant and 2 months of a full commercial expert license. Okay, so here you have the basis as well. So you are all invited and very welcome to be here with us in the beta tester and in the free course, so you will get the experience of performing the course and testing the software. Besides, this International Online CEA Education Center has another courses besides the FreeFEM FEM course, as using ANSYS Workbench and Mechanical APDL software and Patron Astron. In this website, you can check all the available courses. There are self-paced courses, so you can enroll anytime. And well, if you want to get the full FEM knowledge through the International Masters in Theoretical and Practical Application of the Finite Element Method and the CA simulation, you can get both fundamentals and practice with any of the available software, which you can practice any ANSYS, Patron, Apex, CivilFEM. We are currently in our 26th edition, so you can get information and enroll for the next 27th edition, which well, we are already have over than 4,000 engineers who have already studied these masters. Just to let you know that IngeCyber can be your consulting partner. All types of engineering projects can be performed. Nuclear, geotechnical, any type of civil mechanical engineering, including photovoltaic industry, fiber reinforced concrete structures, wind turbine, and soil structure interaction are included in our portfolio. So please ask for any information about our services. Thank you very much for attending to this webinar. Please complete our survey, which will pop up once we finish this webinar. Visit our social media. Here is our contact info. Please stay safe. See you soon.